that one really quick. We'll do Starling's law, and we'll use this one, I guess. So for Starling's law, here we have an effective Starling's law. Important thing is what's passive tension and what's not passive tension. So what started off is they added more and more tension as they went along. Their starting point is down here, and then they consistently pulled on the outside of the heart, and that pulling is shown by this sort of stepwise progression of the passive tension. So you can see here the passive tension is right up here at the bottom of these troughs here compared to where it started down here. So how do you measure that? What you're going to want to do is you're going to want to choose your the bottom of the trough here that's pretty low. I think I'm just going to place it and leave it right there for now. It's relatively small. With the first one, V2 minus V1, we'll have to zoom in some more to be able to see that. Let's do that. And for passive tension, what we're looking at is we're trying to get it towards the bottom of these troughs here to the bottom of these troughs here. And so the amount of increase in passive tension that you've added is 0.01. As you go up to the next one, the amount of passive tension that you add here is right about this point, 0.02. And what I'm doing is I'm putting the cursor as close as I can to the very bottom of those waves. So there's one right there. Now it's 0.04. And we keep moving it outward, and that gives us a measurement of our passive tension that we have. Okay? And you can use the arrow keys to try to get at the bottom of those, or close to the bottom of those waves there, 0.05, etc. For measuring active tension, what you're going to want, so those numbers that you get for passive tension, you can enter them into an Excel spreadsheet. I would just write passive tension at the top here, and then you can write in those numbers. So we had 0.001, well, we had 0 first, right? The very first one. 0.001, 0.002, etc., etc., and keep filling that in. For the active tension, what you're going to want to do is place it so that you can measure the active tension that you might get here, for example. There we have it as 0.01. And then to measure active tension, let's say, of these guys up here, you move the two cursors over until it's measuring the same amount of tension on the two, within this, whether you want to determine how big are these peaks here. And so you can place it so that you're framed between those two cursors. So I'm going to zoom in between two cursors, clicking here, so I can get at it and see it a little bit clearer. There we are. And now I'm going to look at it. What's our active tension here? 0.006. Great. And again, do these. So you're going to want to measure a number of these to be able to get a decent average and be able to plot this out. And so you'll get an average that you have for at least 3 of those different peaks. And then you can take that average and plug it in to this number, plug it in here. So here, active tension. And let's say that you had 0.001 in the first one, 0.006, this is the one we had here, 0.007 here. To plot these two, what you can do is highlight them and then undergo, and then you're going to want to go under charts, and then you're going to want to choose a scatter plot here. And so sometimes those don't appear unless you open up the window a little bit more, which I just did. Hit scatter. And there we have our, that's where we're looking at our plots. And so what we're looking to see is that there's an active change in this. So we can change this to sort of read Starling's law and so on, fitting what the rubric is asking for. So you're looking to see whether there's a change in active tension, or rather a change in active tension as you're pulling on the heart. And this helps to reflect Starling's law. The mechanism behind that is that the overlap of the actin and myosin fibers reaches a greater and greater optimum as you pull on the heart more and more. And so the connection that you can think of here is, we can look at this slide number 7 here, showing our length tension relationship for skeletal muscle. As you pull apart the sarcomeres further and further apart, there's a point at which you have optimal overlap between the actin fibers and the myosin fibers. And in vivo, we're right around in here. And so as we pull on the sarcomeres more and more, in vivo for the cardiac muscle, we're positioned right around here, whereas in vivo for skeletal muscle, we're right at our optimum. So what that means is basically our heart's set up in a situation where it's operating and not generating as much contractile force as it could, but as you pull on the heart, it will actually generate more force. What's the meaning of that? The meaning is because that pulling mimics the passive tension that can be applied to it. You fill up the heart with blood, that's going to add passive tension to it. Pulling on it mimics that kind of passive tension. Because we can't really easily cannulate the great vessel, for example, of the frog and be able to squirt in more liquid there to be able to mimic Starling's law, so we're just pulling on it from the outside to do the same thing. Okay, so that covers a lot of it. You can use this slide to help you to navigate the different types of receptors that we have, muscarinic and beta adrenergic receptors that we have, and then your class you can use to be able to define what these different types of drugs are: atropine, pilocarpine, and so on. So, but just in case they actually don't cover it, atropine is a muscarinic acetylcholine receptor antagonist, and pilocarpine is the agonist for that, for the muscarinic AChR. And then for propranolol is beta adrenergic antagonist, and isoproterenol is a beta adrenergic agonist. Okay, so that you can use to match up to these effects of the sympathetic nervous system and the parasympathetic nervous system. So this is affecting the the sympathetic nervous system, these guys here, and these guys are affecting the parasympathetic nervous system. Okay, I hope that helps.